Formula One car crashes, firefighting, and spacewalks all require a robust strength to resist the extreme conditions that they are exposed to. In the modern day personal health and safety, we depend on the high resistance to weight ratio that only synthetic fibers can provide. In this analysis of one such family of fibers, the Aramids, we will focus in on two of the most renowned, Kevlar and Nomex, whom since their introduction in the 1960s have undergone a silent revolution in modern day health and safety and protection. But what is an aramid? An aramid fiber can be classed as an aramid when 85% of all the amide groups in a polyamide directly connect to two aromatic rings. The behavior of this group of polymers is dictated by the benzene rings that they are derived from. Their properties include notably their insulative properties at high temperatures, their impressive ballistic response, and wield impressive chemical resistance. Firstly, we begin by introducing Kevlar, a para-aramid developed by the DuPont company. As a result of the functional groups occupying the para positions on the planar benzene ring, the chain is forced into the trans orientation to reduce the steric hindrance experienced. This produces a polymer that is almost perfectly crystalline. These rod-like polymer chains offer Kevlar fibers a low strain, lengthening to only 5% of the original length of the fiber, giving Kevlar a Young's modulus comparable to steel, while only being a sixth of the density. In addition to this, Kevlar chains form hydrogen bonds and pi stack together to form microstructures called microfibrils and pleated sheets, which further improve the load transfer and stiffness of the fibers. These forces maintain cohesion in the crystalline structure when subjected to force. Here, see a demonstration of Kevlar's abrasive resistance. I can score these Kevlar gloves without them being damaged, in comparison to standard rubber gloves which I can easily cut under pressure. This shows how Kevlar fibers are maintaining their integrity despite being subjected to strong shearing forces. Now we must speak about Nomex. Despite being identical in composition, it has a lower density and tensile strength. This is because of the meta positions being occupied on the benzene ring, which creates an opportunity for variation in the crystal structure of Nomex. This is because the connecting groups can occupy the 4 or the 6 position on the benzene ring. Since there is no preference to adopt a strict cis or trans configuration, this develops many amorphous regions throughout the polymer, with only the first 2% of a polymer chain being continuously uniform, which reduces the tensile strength of the Nomex, leaving Nomex able to stretch to up to 35% of its original length under tension. Despite Nomex just sounding like a worse Kevlar, there are places where a lower weight, high heat resistant, and high chemically resistant fabric can still make Nomex a viable fabric for use in clothing in comparison to solely using Kevlar, which is heavier, and in jobs like firefighting where equipment can weigh up to 36 kilograms, the lighter the better. Following on from firefighting, the aramid fibers are notably fire retardant, with Nomex degrading above 500 degrees Celsius, something very unusual for synthetic fibers, and Kevlar maintaining 50% of its tensile strength at 300 degrees Celsius. This is thanks to the fibers swelling when exposed to fire and heat, and is caused by the charring of the outermost fibers, which form a thick layer of carbon, and sufficiently insulate the wearer, protecting them from high temperatures. To demonstrate the fire retardant properties of Nomex, I have compared it with some standard cotton string, which catches fire rather quickly, where Nomex is left unaffected. This is due to the limiting oxygen index of Nomex being about 28%, meaning that in order for Nomex to catch fire, the proportion of oxygen in the air or in the fiber needs to be raised by 6%, something which only happens at higher temperatures, making aramid fibers invaluable for protecting the wearer. The synthesis of these fibers is almost as important as the structures themselves, as if the fibers are too short or disordered, the polymer may become weaker. Kevlar and Nomex are synthesized via a step growth polymerization between an aromatic diacyl halide and an aromatic diacyl amine to form a copolymer. The complicated part of forming these viable Kevlar fibers is that at Kevlar's glass transition temperature, Kevlar is more likely to decompose than go into the rubbery state. Therefore, traditional polymer melt spinning is not viable. To get around this complication, Stephanie Kolek and other DuPont chemists developed a technique called wet spinning, which kept the Kevlar dissolved, which posed difficulties in and of itself, as the Kevlar is virtually insoluble, as the strong hydrogen bonding and straight chains cause the polymer to crystallize out of solution above certain concentrations. To avoid this, calcium ions interrupt the hydrogen bonds and behave like plasticizers. To avoid the complications as mentioned prior, the Kevlar is synthesized dissolved in solution, with each component being added stepwise under nitrogen with the calcium ions previously mentioned in solution. These fibers then undergo heat shearing, and the solution is launched out of a spinneret into a coagulating bath, where the Kevlar fibers solidify and are collected, before they are sent off for further processing and distribution to other machines that weave the Kevlar into denser fibers or laminates. Ultimately, with regards to Kevlar and Nomex in terms of research, I think it's safe to say there is still room. With Aramid nanofibers being used to produce things like aerogels, battery separators, and flexible electronics, the future is in close view for this area of materials science. However, I believe Kevlar will be a specialist fiber for transport in the near future, solely based on price, with it being further incorporated into automotives and airplanes that will make components have a longer lifetime and make chassis lighter, which will reduce the long-term operating costs of transportation. With the exception of this rule, for us, in our day-to-day life, being the occasional usage for shock value like bulletproof bathrobes, or more frighteningly, Kevlar laminates in backpacks. Thank you for watching my video on the Aramid fibers.